Let's now learn about the second shifting or translation theorem. We need this theorem to find the Laplace transform of a function that isn't a constant and turns on at a specific point in time. Let's look at an example. We want to express f of t using a unit step function and then find its Laplace transform. Our function f of t is equal to t when t is greater than or equal to 0 but less than 3, and then at 3, it's equal to 0. Let's graph our function. We'll put f here, and we'll put t here, and we'll let this point be equal to 3. Our function is going to be equal to t between 0 and 3. So we'll put an open circle here at 3, we'll put a closed circle at 0, and a line in between. And then at 3, we'll put a closed circle, and it's equal to 0. Let's now write f of t using a unit step function. We'll start with f of t, and notice that it starts with t, so we'll say that it is equal to t, and then we have to turn this t off at t is equal to 3. So we're going to subtract t times u of t minus 3. Let's now find the Laplace transform. The Laplace transform of f of t is the Laplace transform of t minus the Laplace transform of t times u of t minus 3. The Laplace transform of t is equal to 1 over s squared, and then we need to find the Laplace transform of t times u of t minus 3. We actually don't know what this is. We know the Laplace transform of just u of t minus a, but we don't know the Laplace transform of a function times u of t minus a. The second shifting theorem is going to tell us what this transform is. Before we talk about the second shifting theorem, you might be wondering, well, what is the first shifting theorem? The first shifting theorem tells us that the Laplace transform of e to the at times f of t is just f of s minus a. The exponential shifts the transform in the s domain, and s becomes s minus a. The second shifting theorem tells us that the Laplace transform of f of t minus a times u of t minus a is equal to e to the minus as times f of s. This delay in time, represented by this a and this a, becomes a factor of e to the minus as, that's right here, in the s domain. The key to using this theorem is to be able to take your function f of t and change it to a function of t minus a. We're going to do that right now. Let's go back up here to our example. What we need to do now is evaluate this Laplace transform, and we can do that with the second shifting theorem. We had the Laplace transform of f of t was equal to the Laplace transform of t minus the Laplace transform of t times u of t minus 3. We already saw that the Laplace transform of t is 1 over s squared. Now we're going to use the second shifting theorem to evaluate this Laplace transform. What we're going to do is we're going to replace t with t minus 3. So we're going to say that t is equal to t minus 3, and we can't change it, so we have to then add 3. That way, we have our t minus 3, and then we have a constant, and we know how to work with both of those. So this becomes minus the Laplace transform of t minus 3 times u of t minus 3, I'm splitting it up, plus 3 times u of t minus 3. Now this is equal to 1 over s squared minus the Laplace transform of t minus 3 times u of t minus 3. So this is just e to the minus as, which is 3s, times f of s, which is the Laplace transform of t. And then, making sure to carry our negative through, we have minus 3 times the Laplace transform of our unit step function, and that is e to the minus 3s divided by s. This gives us 1 over s squared minus e to the minus 3s divided by s squared minus our 3e to the minus 3s divided by s. Let's combine our s squared terms, and we have 1 minus e to the minus 3s, all divided by s squared, and then we have minus 3e to the minus 3s divided by s. And there's our Laplace transform. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.